In this video, we'll cover section 4.5, which goes over the graphs of our two most basic primary trig functions, sine and cosine. Unfortunately, this is, like I kept saying in a lot of the earlier sections, this is the last section that they really consider that you should basically know. So we'll go through this a little bit quickly, but then we'll realize that in 4.6, we'll talk about the graphs of the other four trig functions. Tangent, as we've kind of seen, kind of is its own little case. But then for secant and cosecant, we'll realize that the graphs of sine and cosine are the keys to those new graphs as well. So the first thing, what are the graphs of sine and cosine? I'm going to give you a quick reminder. Instead of just jumping right to the graphs themselves and the properties, let's get a few reminders why these are the way that they are. And I'm going to use the idea of the unit circle. That when we had angle theta measured in the standard position, starting from the positive x-axis, going in our counterclockwise orientation, and that if this is a unit circle, that the x value represents the value for cosine at angle theta, and that the y value represents the trig function sine at angle theta. Let's start with this one first. That if I want to look at the graph of y equals sine theta, I'm treating this like the y-axis as always, but now instead of this being the x-axis, I'm going to use the variable theta. So that way, literally, I could go off of this graph to figure out what's happening here. This is why some people get a little bothered by the trig functions, that we've got a graph of the function, but we also have another picture that's trying to give us information. But what I'm using, I'm looking at theta, what is my angle theta, and what is the y that goes with it. So I'm going to start when theta is 0, and what's the y value right here? Well, the y value is 0, meaning that this has a point on the origin. But now, as I look at positive values for theta, well, first I keep going up, 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 and then right here, my y value hits its highest point. Its highest point is 1, and it reaches that point at this angle, which would be 90 degrees. The book loves doing this with radians, everybody, but like I always say, I'm perfectly happy if you just do it in degrees. So I'll use 90 degrees, same thing, and the book uses pi over 2 radians. So we started here, and we went up, 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 and then when we got to 90, we hit that peak. But now as I keep going past 90 degrees, my y values start going back down. Until I get to here at 180 degrees, my y value is back to 0. And now we keep going. Now I'm here. So I keep going past 180 degrees. Now my y values are actually becoming negative, and they're the lowest, the most negative they can be right here. So that at 270 degrees, trying to make sure this is accurate, this would be a y value of -1. And we wrap around the circle, and back to 360, we're right back where we started. We're back at a y of 0. But now, this is not the only part of the sine graph, because as we've seen, angles go past 360. But if I go past 360, everything I did just keeps repeating. So I keep just repeating that as I keep going to the right. I would go up to 1, down to -1, up to 1, down to -1, and that would repeat forever to the right. Similarly to the left. If I had negative angles, well, now I'm just going in the opposite direction. So I'd start with negatives. So all of this leads us to two things. Number one, that the sine graph doesn't just start here and finish here, that it keeps going beyond in both directions. But we refer to sine, and similarly we'll see in cosine in a moment, that we refer to sine and cosine as periodic functions. Because even though they keep going on forever, they eventually repeat themselves. That when I get back to here, I'm repeating what happened starting right here. If I go back to here, this is a cycle that repeats exactly what happens right here. So we keep getting sine, and sine has multiple cycles. But when I go to ask you to graph these functions later on, I will always tell you to label all the important points for one cycle. That's what I have here. The important y's, the high and the low, and all the important x's. The x's where we hit our peaks and our valleys, and where we cross the x-axis, our midline. So that will be one cycle that's completely labeled. And then in any other direction, give me more of the graph. So that way we don't make the mistake and think that sine literally starts here, finishes here. And even though that's normally what we're looking for, that has all the highlights, that considers one lap around the unit circle, but we always want to realize that the graph keeps going. So that's our sine function. And now if I just get rid of this and now I call this x, that becomes y equals sine x. Again, I wanted to use theta so we didn't confuse the x value over here. But now I'm going to do almost the same thing, but now I'm going to focus on cosine. Still thinking about this, but now I'm going to make my graph x equals cosine theta. So even though this is traditionally the y-axis, I'm treating it like it's the x-axis, and this is the x-axis, but I'm still going to treat it as the theta axis. And just like we said at the end, after I get this picture, then generically this will be y equals cosine of x. But I'm up here, I'm thinking about this, but now I'm focusing on the x values as I go around. And here's the biggest difference. Right off the bat, when theta is 0, we're right here, we're literally looking at this point on the unit circle, the x-coordinate is 1. So in a lot of ways, people think about the beginning, cosine starts up here. Now what happens to x as we start looking at bigger values of theta? Well, by the time I get to here at 90 degrees, x is 0. And then as I go past 90, now my x's are negative. And then this is the biggest, most negative x value right here. At 180 degrees, the x is negative 1. Keep going. X is still negative, but by the time I get to 270, I'm back to 0. And then I wrap around and finish right here at 360, and I'm back up at a value of 1. So this will be one cycle of cosine, but everything we said for sine, this still continues. This is just one cycle, but then if I keep going, that would go down and up and so on, and this way, back down. So sine and cosine at their most basic, still those cyclical functions, and that they keep repeating over a certain period. And these are the basics. So a lot of you hear people talk about the sine curve and the cosine curve. That's what they're referring to in their most basic forms. Now, if you go back a little bit, we were doing a lot of those basics, and even back in the unit circle, our book was pointing out that sine was odd and cosine was even. I mentioned that back in the notes, but really I want to bring it up right here. Look at this. This has all the properties of an odd function. It's got that symmetry across the origin. What happens for the positive x positive y is the complete opposite for the negative x negative y. So that gives us sine of negative x is equal to negative sine x. It's using that odd property. And now, again, looking at the graph, we could point out it was a fact back here that if you do this angle, you get a positive y, but if you do the negative angle, the same y, but the y value is now negative. So we could have pointed it back here the way the book did, but I thought it was easier to show it with the graph. Similarly, that cosine is even, that we have the nice symmetry across the y-axis, that this is the mirror image over here, that this is the mirror image over here. So that I would have cosine of negative x is equal to cosine x, using the whole f of negative x is equal to f of x. That's the definition of being even, and we're seeing it here, so that's the property we get. Remember, everybody, we always said there are lots of properties that can come up here. So just pointing out a couple to realize why they are what they are. But the biggest thing is that these are the basic graphs for sine and cosine. But now we've said a couple of things. Let's add a tiny bit more to them. This idea of the highs and the lows, that both of these have highs and lows of 1 and -1. That is what we refer to as the idea of the amplitude. In a trig function, sine and cosine, the literal definition of the amplitude is half the distance from the highest point to the lowest point. But look at how that works. Literally, the highest y is 1, the lowest y is -1. So the total distance from the highest to the lowest is 2, and half that distance takes us back to 1. So literally, that idea of amplitude is how high we go above the midline for the peaks and how far we go below the midline for the valleys. That's the idea of amplitude. And in either one of these, that would happen by getting a multiplier out in front. If this was 4 sine theta, I'd go up to a high of 4 and a low of -4. If this was 2 cosine theta, the high would be 2 and the low would be -2. It's a very nice property, and all that comes from the keyword amplitude. And we also mentioned the idea that these graphs repeat themselves. The period is the duration it takes for them to repeat themselves. The basic sine and cosine, these have an original period of 360 degrees. Or again, I know the book goes nuts with the radians here, so they note that it's 2 pi radians. Just go back for a second, everybody. Again, the book would do this, and instead of having these x's, thetas in terms of degrees, they would just do it radians, pi over 2 pi, 3 pi over 2, 2 pi. And the same exact thing right here. Okay, so that's the original period, but we'll realize inside the theta that if there's an extra multiplier inside of here, that's what affects the period. So that we will always take the original period and we'll get our new period by taking the original one and divide by k. And the k would come up inside of here. That if I had sine kx or sine k theta, that's the k we're talking about. And this is a little tricky, everybody, because if I look at sine 3x, my period, my new period, would be 360 divided by 3, which would equal 120 degrees. Okay? It's a little misleading because some people think, well, if k is big, that should make the period bigger, but it's the opposite. What's literally happening here, what typically happens without the 3, you need to plug in the whole 0 through 360 to get all those angles that cover one lap around the unit circle. But now having that extra multiplier, everything speeds up. So by speeding up, it takes a shorter time to get through everything. If this was something like sine of 1/2 x, now I do 360 divided by 1/2 and get 720 for the new period. So it's a little misleading. People think by having a number k equal to 3, they feel like the period should get bigger, and by having k be 1/2, the period should get smaller, but it's the opposite. When we go to put the graph together, those are the two big things that we're looking for. The highs and the lows that come from the period, and all these important x values that come from the period. And here's the last thing, everybody. They all have nice, I don't want to use the whole word symmetry because we've used symmetry before, but things happen in equal increments here. That if the period gets shorter, that if it only takes 120 degrees, well, it doesn't go 90 to 120 and you're done. You've got to hit all the highs, the middle, the lows, and back to the middle, and it all happens in equal increments. So if my new period is, say, 120, well, this all happens in equal increments. It would take half of this to get to the middle, that would be 60, and then half of that to get to the peak, and then this would be another one of those intervals. So a lot of people, once they get their new period, they always realize there's 4 important spots. So they take that period divided by 4 to get their interval. So that the interval, everything important happened every 30 degrees. 30 degrees for a peak, 60 degrees back to the middle, another 30, so 90 degrees to the minimum, and then another 30, so 120, and we finished our picture. The last thing before we start graphing, everybody, is just to realize, if we kept putting all these graphs on the same graph, I mean, all the different changes. Now, all of a sudden, this is going up to 4, down to -4. So extreme highs and lows. Or now I have to finish the whole graph by the time I get to here. Up, down, back to the middle. So all these things compress, stretch these graphs. But here's the real nice thing, everybody. When we're making these graphs, we'll make the graph first. Keep everything nice and neat. Make these nice round smooths. Notice there's no boxes here. This is not a hard box. These are not V's. Smooth hill tops and hill bottoms. And again, symmetry. It's not a big hill here and then a quick little small hill to finish. That this hill that's above the x-axis here is kind of balanced out by this hill below the x-axis over here. So we'll do all that nice and neat, and then we'll come back and fill in the numbers. What is the high Y? What is the low? What are all the important X's? That's going to be our good way to construct these. And even though these are the 2 new things, we're definitely always interested in these, we could still have little things like shifting a graph up, down, left, right. A negative out in front still reflects across the x-axis. So let's take a quick minute or 2 to do a couple of quick sine and cosine. And then again, we'll see the next section, how we'll use these to graph the other trig functions. Okay, so I said this at the beginning, but let's write it out formally. Now we're going to sketch the graphs, but a few little extra things. What am I looking for? I want to sketch at least 2 cycles, labeling all the important values for 1 cycle. And the important values, like we kept mentioning, that you're going to need the amplitude to identify the highs and the lows, and the period to then get that increment to get all the peaks and valleys on the x-axis. So let's start off with y is 3 sine of 2/3 x. Well, this gives it away right off the bat. The amplitude is 3. So that means my highs are going to go up to 3, my lows are going to go down to -3. This does not give me my period, but that's the k value that gets the key to finding my period. That I would have k is 2/3, so the new period would be the original 360 or 2 pi. There's nothing wrong with doing this with 2 pi, everybody. I'm just choosing to stick with the degrees. Divided by 2/3, so 360 times 3/2, so we'll end up getting 540. And that's it. I'll come back. I wanted to do this as a quick warm-up, but then I want to show you a few little tweaks on it and how it's cosine and so on. So if that's all I have, well, that's all I need. I'm going to graph. There's 1 cycle of sine, and that's the cycle I'm going to label. But now at least give 2 cycles. So at least give a little more over here. You could do a second whole cycle over here. Maybe do a second whole cycle over here. Maybe do a piece of this and a piece of this. Again, everybody, I just want us to realize that the graph literally doesn't just start and stop here and here. That's the reason I'm putting this extra piece. So there's multiple cycles, labeling all the important values for 1 cycle. Well, the high is 3. And the low is -3. I mean, do you see what I did? This is a much smaller graph than I drew here, but I'm controlling the scale. So I can literally draw 3 dashes up, 3 dashes down, but even just getting the point. The highest one is 3, the lowest is -3. And I'm doing my best, everybody. You might argue that's a little closer to the x-axis than that is, but it's decent enough. It's not like I said, that's 3, and that's -3, something where my scale is so obviously flawed. That's definitely close enough. I started here at 0, so all the way to here, that would be 540. That's the new period, so that's what it took to complete one full cycle. Same thing, everybody. Now all of a sudden that represents 540 degrees. Before that only represented 360. I'm controlling the scale. If I always drew all my trig functions on the same graph, I'd have these tiny ones that just here, these ones that go extremely high up and down, ones that need to extend so much further. So we'll create the scale. So I jump to the end, that's 540. I could do 540 divided by 4 to get my increment, or I could go slowly just to realize, well, here is half of the interval, so half of 540 is 270. So a lot of ways to go, and then half of this to the peak, that'll be 135. Well, 135 plus another 135 plus another 135, we'll get that to 405. That is full credit for that type of a problem. But now, like I said, I just want to play a few games on this. What if this was y equals 3 cosine of 2/3 x? This information is all identical. So all I'm going to do is just when I sketch, don't sketch the basic sine curve, sketch the basic cosine. Start at the peak. Go down and up and back and keep doing it, right? So that we get multiple scales. Over here and over here, it's easy to almost make these like V's again. Just because it stops here, I still need the hill to get to the peak and then another part to keep coming down. I probably did that a little too tight here, but again, this gets me through one here to here. That's one full cycle of cosine. From the peak all the way down back to its peak. And its peak is still 3. The valley is still -3. The period is still 540. But now this would be the 135. This would be the 270. This would be the 405. So I still needed that same information. I just made the cosine curve and then filled that basic information in the same way. Okay, 2 more little things. Let's look at y. Let's do -3 sine 2/3 x. And then we'll do y is 3 sine 2/3 x minus 1. I'll mention one other quick thing here, but this is where we're going to wrap up this video. What does this extra negative do? Negative out in front flips over to the x-axis. So what's different about the graph of this compared to the graph we had here? The flip. So all I would do when I graph this, I'd note that reflection across the x-axis, right? Those are definitely things we're still looking for. But now when I draw my sine curve, I just start in the middle and do the bottom loop. I do the bottom loop and then the up loop instead of the top loop followed by the bottom. That's all. High is still 3, low is still -3. We've still got the 540. So again, same increment, 135, 270, 405. I'm probably a little squeezed here. That's not quite as wide as this one. But again, close enough. That's good. What about this one? Well, all that same basic stuff, but this -1 at the end would pull everything down 1. If I had a plus or minus on the inside, we'd still have left rights. Just realize k has to be factored out. So if I just literally had x minus 30, well, that's 30 degrees that I have to be shifted to the right. But if I had 2x minus 30, I'd have to pull the 2 out. So the 2 would be the k, and then it'd only be 15 would be my shift. But this one is on the outside, so that's up, down, left. I'm sorry, up or down, so that would be specifically down 1. So now back to this graph, but everything just goes down 1. So what changes? The highs and the lows. That's it. Instead of having a high of 3, everything goes down 1. So now the high is 2. Instead of having a low of -3, everything goes down 1. So now my low is -4. But don't draw it evenly, everybody. 2 and -4 are not equally close to the x-axis. And realize that the x-axis in my originals always served as the middle of the graph. That halfway between a peak and a valley, the middle, well, this coincidentally landed on the x-axis. Now my middle line was shifted down 1, so I'll just make a little bit of a dash line here. And that would go with y equals -1. Treat this like the original x-axis. Now I'd make my sine curve up to the peak, down to the middle, down to the valley, back up to the middle. There's one cycle. Again, show me a little more, but that gives you the one cycle. Your important y's are labeled. How about your x's? Well, this, be clear here, these are no longer important. This is still an important point because it goes with the max, and that's still the 135. Some people still want to label these on the x-axis because that's a traditional way. I mean, honestly, some people, they just like to label the xy pairs. I like to put my labels on the xy axes, but it's all giving the same information. It's whatever you prefer. But just realize this is the spot. And then especially this one, it's not here, it's here. It's where I cross this line, here. Then it would be here, and then it would be here. Even if I keep drawing, it's not where I cross the x-axis. It's, again, where I cross my midline. So here's the 135, 270, 405, and then 540.